Hi to everyone. Today I would like to explain about the correlation between the two random processes x of t and y of t. Hence, in this video I am going to covering the contents are autocorrelation function ACF, cross-correlation function CCF and covariance function. These three are going to describing about the relation between the random process x of t and y of t. First, we will say about the autocorrelation function. What is meant by autocorrelation function? It is defined as what is the similarity or coherence is there between a random process x of t and the delayed version of x of t. Suppose if you are going to taking something random process x of t at particular time say t1 and at other time say t2, x of t2. How much of similarity or coherence is there between these two random processes? We are going to explaining by using the autocorrelation function. It is indicated as Rxx of t1 comma t2 is equal to E of x of t1 into x of t2. E stands for expected value. Here we are going to calculate the expected value of a random process at the two different times t1 and t2. So, this is the equation of the autocorrelation function. In terms of integration, it is indicated as integral minus infinity to infinity, integral minus infinity to infinity, x of t1 into x of t2 dx1 dx2. Here we are taking a random process x of t at two different times. So, thus we are doing the integration two times in the range of from minus infinity to plus infinity. And the integration with respect to dx1 as well as the dx2. For the case of WSS process, WSS stands for wide-sense stationary. In the last video, we have seen that for the case of wide-sense stationary process, its corresponding autocorrelation function is constant. Why? Because let us consider t1 is equal to t and tau is equal to difference of the two times t2 minus t1. If tau is equal to t2 minus t1, then t2 is nothing but tau plus t1. This is written as t2 is equal to tau plus t1 or t1 plus tau. We have assumed t1 is nothing but equal to t. Substituting this here, we are going to getting as t2 is nothing but t plus tau. Therefore, Rxx of instead of t1 represent as t, instead of t2 substitute as t plus tau, then this entire is nothing but Rxx of t comma t plus tau is equal to E of x of t into x of t plus tau. This is equal to simply Rxx of tau only. That means for the case of wide-sense stationary process, the autocorrelation function is function of tau only. It does not depend upon the time t1 and t2. It depends upon the tau means it is the difference of the time t2 minus t1. This is the definition of the autocorrelation function. Then coming to the properties of autocorrelation function. The first property is, you can see here, E of x square of t is equal to Rxx of 0. What is E of x square of t? It is nothing but the mean square value. E of x of t is known as the mean value. Square of a random process is x square of t. For that, if you are going to calculate the expected value, that is known as the mean square value. The mean square value of random process x of t is equal to the Rxx of 0. Rxx of tau is nothing but the autocorrelation function. If we putting tau is equal to 0, then that is nothing but the value of the ACF at the origin. That means, for the first property describes that the mean square value of a random process is equal to the autocorrelation function value at the origin. This is also giving the power of the random process. That means the first property describes that it is going to giving the power of a random process which is equal to the autocorrelation function at the origin. Then coming to the second property, mod Rxx of tau is less than or equal to Rxx of 0. Here it is going to give in the mod of Rx out of is less than or equal to means it is going to give in the boundary value. That means autocorrelation function is having the maximum at the origin. And the third property is Rxx of minus tau is equal to Rxx of tau. Here in the LHS you can observe that tau is replaced with minus tau, but the minus is not present in the RHS. That means it is going to satisfying the symmetry. Specifically, it is satisfying the even symmetry property. That's why autocorrelation function is known as the even function of tau, because we are going to replacing tau with minus tau, but at the RHS we are not getting that tau. Rxx of minus tau is equal to Rxx of plus tau only. Next one is limit mod tau tends to infinity, Rxx of tau is equal to x bar square. X bar is known as the mean, and for that square here we are going to getting. And here the conditions are, we are going to defining a random process x of t with a non-zero mean value. That means x bar is not equal to 0, or e of x of t is not equal to 0, and it is a ergodic with no periodic components. Coming to the next property, if x of t is periodic, then autocorrelation function is also periodic. That means if the random process is having something period, say t, then ACF is also having the same period. Sixth property is limit mod tau tends to infinity, Rxx of tau is nothing but equal to 0. In the fourth case, you can see that for the case of non-zero mean value, it is equal to x bar square. Now, in the sixth property, if we are going to consider x of t is ergodic process with a 0 mean, that means x bar is equal to 0. By substituting x bar is equal to 0 here, we are going to getting yes, this is sixth property, that is limit mod tau tends to infinity, Rxx of tau is nothing but equal to 0. And the last property is nothing but autocorrelation function of a random process, Rx of tau cannot have any arbitrary shape. That means we may have different types of shapes like sine waveform, square, etc., what it may be. But for the case of ACF, it does not contain particular shape. Based on the random process nature, it contains its own shape. So these are the 7 properties of autocorrelation function. Once again we will see the first property is nothing but E of x square of t is equal to Rxx of 0. Second property is mod Rxx of tau is less than or equal to Rxx of 0. Third one is Rxx of minus tau is equal to Rxx of tau. Fourth one is limit mod tau tends to infinity, Rxx of tau is equal to x bar square. Fifth one is if x of t is periodic, then ACF is also periodic. Sixth one is if x of t is having 0 mean value, then limit mod tau tends to infinity, Rx of tau is equal to 0. And the last seventh property is if Rx of tau, if you are going to describe it, it does not contain any arbitrary shape. These are the 7 important properties of autocorrelation function. Next, coming to the topic of cross-correlation function. What's the definition of cross-correlation? The name itself tells that we are going to correlating. Cross means between two random processes x of t and y of t. Here in this case, we are going to measuring the similarity or coherence between the two random processes. So thus the notation for cross-correlation function is Rxy of t1 comma t2. That is equal to, the formula is expected value of x of t1 into y of t2. In the previous case autocorrelation function, we have defined same random process at 2 different times, t1 and t2. But here 2 different random process x of t1 and y of t2 at 2 different times t1 comma t2. Their expected value is given as the cross correlation function. it will describe the how much of correlation is there between the two random processes. Next, the formula for the case of cross-correlation function in terms of integration is integral minus infinity to infinity, integral minus infinity to infinity, x of t1 into y of t2 dx dy. Now here two different random processes are there, that's why we are taking as dx dy. We are doing the integration with respect to x first and then to the y. First we are doing with respect to x means this integration is corresponds to x and this corresponds to y. Then for the case of WSS process, that means wide sense stationary process, let us consider T1 is equal to T, tau is equal to T2 minus T1. Then from this T2 is nothing but tau plus T1. So that's why T2 is equal to T1 plus tau, that is equal to, by instead of T1 substitute as T plus tau. Then substituting this T1 values and T2 values in the above equation, we are going to getting as Rxy of T comma T plus tau is equal to E of x of t. Instead of T1 replace with T, instead of T2 replace with T plus tau. That's why E of x of t into y of t plus tau. That is equal to Rxy of tau. That means it is a function of the time difference tau is equal to T2 minus T1 only. It does not depend upon the time T1 and T2. This is about the cross correlation function definition. Then coming to the properties of cross correlation function. Suppose if you are dividing the two random processes x of t and y of t, and respect to cross correlation function is nothing but Rxy of tau, or even you can define Ryx of tau also. We can interchange x and y. That will become another cross correlation function. From that, the first property is nothing but Rxy of tau is equal to Ryx of minus tau. That means here that tau is replaced with minus tau. Okay, both are equal, but here you can observe a point. Here xy is there, but here yx is there. X and y are interchanged. That's why, hence minus is not there in this case. This is known as the symmetrical property. But x and y are interchanged, hence it is not a even symmetry. Suppose if x and y are not interchanged, then that is known as the even symmetry. Like in the case of previous autocorrelation function, Rx of minus tau is equal to Rxx of tau. That means it is going to satisfy the even symmetry. But now in the cross correlation function, since x and y are interchanged, it is satisfying only symmetrical property only. This is the first property of the cross correlation function. Next one is, if Rxx of tau and Ryy of tau are the autocorrelation functions of x of t and y of t, then they are going to satisfying one of the inequality equation. That is, mod Rxx of tau is less than or equal to square root of Rxx of 0 into Ryy of 0. So this is nothing but the cross correlation function indicating the inequality symbol less than or equal to giving the boundary value. This RHS is square root of Rxx of 0 into Ryy of 0 is known as the geometric mean of autocorrelation functions of x of t and y of t at the origin. So Rx of 0 is the ACF value at the origin, Ry of 0 is the ACF value of y of t at the origin. This entire is nothing but the geometric mean. Hence here you can tell that this corresponding mod Rxy of tau is less than or equal to geometric mean of Rxx of 0 and Ryy of 0. It is bounded with its value. So this is the second property of cross correlation function. Coming to the next property, one more inequality equation is there, that is mod Rxy of tau is less than or equal to 1 by 2 into Rxx of 0 plus Ryy of 0. You can observe that this is nothing but the arithmetic mean. So now in this case, the cross correlation function Rxy of tau is less than or equal to arithmetic mean of two random process x of t and y of t at the origin. So two boundary values are there for the case of cross correlation function. Previous one is nothing but the geometric mean. Now it is the arithmetic mean. Coming to the next one. If two random process x of t and y of t are statistically independent, if that is the case, then they are WSS process. That means Whitson stationary. In such case, Rxy of tau is equal to E of x into E of y. That means the cross correlation function is equal to the product of individual expected values. It can be simply written as x bar into y bar. These are the four properties of cross correlation function. Once again, you can see that the cross correlation function is going to satisfying simply symmetrical property, and it is having the two boundary values, and the last one is for the case of statistically independent random variables. Next topic is covariance function. For the case of two random process x of t and y of t, we are going to defining two types of covariance function. If you take a single random process x of t, for that we will define autocovariance function. It is indicated as Cxx of t comma t plus 1. That is equal to E of x of t minus E of x of t into x of t plus tau minus E of x of t plus tau. Recall all of you, for the case of variance, the formula is given as sigma x square. Sigma x square is nothing but E of x minus x bar whole square. And if you take the covariance, that is Cxy is equal to E of x minus x bar into y minus y bar. Similarly, here in the case of random processes, we are taking the same random process at two different times. One is at t, other one is at t plus tau. So that's why here we have defined the covariance function E of x of t minus E of x of t into x of t plus tau minus E of x of t plus tau. This entire expected value will give the covariance of the random process x of t. It is also indicated as Cxx of t comma t plus tau is equal to Rxx of t comma t plus tau minus E of x of t into E of x of t plus tau. Suppose if x of t is WSS, that means Whitson stationary, then Cxx of t comma t plus tau can be represented as simply Cxx of tau. That is equal to Rxx of tau minus x bar square. For the case of WSS, E of x of t is equal to x bar and E of x of t plus tau is also x bar. So, x bar into x bar is nothing but x bar square. So, this equation is simplified as simply Rxx of tau minus x bar square for the case of WSS process. At tau is equal to 0, Cxx of tau can be represented as simply Cxx of 0, that is equal to, substituting tau here, Rxx of 0 minus x bar square. From the properties of autocorrelation function, Rxx of 0 is nothing but E of x square. That is substituted, then this equation is E of x square minus x bar square. So, this is nothing but generally the variance of the random process indicated as sigma x square. That means for the case of WSS process, the covariance will become as variance. For the case of WSS process, the covariance is become as simply variance. That means Cxs is equal to the sigma x square. This is about the autocovariance function. Then coming to the next topic is cross-covariance function. The cross-covariance function is defined as for the case of two random process x of t and y of t. The notation is Cxy of t comma t plus tau. It is equal to the e of x of t minus e of x of t into, now consider the second one is nothing but y. Y of t plus tau minus e of y of t plus tau. By taking expected value for this entire, we are going to getting the cross covariance function of two random process x of t and y of t. In terms of cross correlation function Rxy, we can represent Cxy is equal to Rxy of t comma t plus tau minus e of x of t into e of y of t plus tau. That means cross covariance function is equal to the cross correlation function minus product of individual expected values of the random processes x of t and y of t. For the case of WSS process, that means white and stationary, what will happen for the case of x of t and e of y of t plus tau? Both are equal to simply e of x and e of y only. That's why Cxy of tau is equal to Rxy of tau minus e of x into e of y. Then come to the last one. Suppose if x of t and y of t are uncorrelated, that means there is no any relation between the x of t and y of t. That is known as the uncorrelated. If there is no any relation, in such case, what will happen? Anyhow, this corresponding correlation function is becoming as simply e of x into e of y. Both are get cancelled. Then we are going to getting as the covariance function Cxy of t comma t plus tau is equal to 0. For the case of uncorrelated random process x of t and y of t, its cross covariance function value is nothing but equal to 0. So this is about the covariance function, autocovariance function as well as the cross covariance function. Based on this, we are going to defining some more new parameters. In that, the first one is autocorrelation coefficient. By using the autocovariance function, we are going to define this one more new parameter. It is indicated as rho xx of t comma t plus tau is equal to Cxx of t comma t plus tau whole divided by square root of Cxx of t comma t into Cxx of t plus tau comma t plus tau. Here in this case, you can observe that numerator is nothing but the autocovariance function of x of t, and denominator is nothing but the, this is square root of, this is nothing but the autocovariance function of the x of t at a time t, and this is nothing but at a time t plus tau. All this consisting of the autocovariance parameters, hence the respective coefficient is nothing but the autocorrelation coefficient. It will give the relation between the all autocovariance parameters. The next one is the cross correlation coefficient of the two random process x of t and y of t. The notation is nothing but rho xy of t comma t plus tau is equal to Cxy of t comma t plus tau whole divided by square root of Cxx of t comma t into Cyy of t plus tau comma t plus tau. This is the cross covariance function of x of t and y of t, and this is the autocovariance function of x of t at t is equal to t, and this is the autocovariance function of y of t at t is equal to t plus tau. So here it consisting of autocovariance function as well as the cross covariance function. It will give the relation between the both covariance functions. That is nothing but the cross correlation coefficient of two random processes x of t and y of t. Thus, in this video, I have explained about autocorrelation function and its properties, cross-correlation function and its properties, and covariance functions as well as its correlation coefficient. Thank you.